Hello, this is Mark Scythian, FAA licensed aerospace technician, airframe, power plant, and avionics certified. The date today is June 28, 2016. In this video lecture, I will be explaining how to properly calculate the power output that you can use in regards to a four-stroke gasoline piston engine. In a four-stroke gasoline piston engine, there are four stroke cycles of the piston. There is an intake of air and fuel, compression, power, and exhaust connected to a connecting rod, which then connects to a crank pin to transmit dynamic force from linear into angular rotational work. On the intake stroke, both air and fuel are drawn in the form of gaseous vapors. Then an intake valve will close during the piston cycle on the upstroke. On a four-stroke gasoline piston engine, there are four-stroke cycles of the piston, for which 2 revolutions of the crankshaft occur during every power stroke. So you have air and fuel intake, compression, power, and exhaust. Connected to the crankshaft through a timing chain or belt is a camshaft, which rotates usually at 1/2 the RPM of the crankshaft. The camshaft's job is to open and close the intake and exhaust valves using cam lobes that transmit linear force by rotation. So when the piston comes down on the intake stroke, the intake valve will start to open at its full position by the time the piston is about halfway down through the cylinder. When the piston starts to move upward on the compression stroke, both the intake valve and the exhaust valve will be closed. This allows the fuel-air mixture that's drawn in to be compressed. Then the fuel-air mixture is ignited just before the piston reaches the top of the cylinder or top dead center. By the time the piston moves to top dead center and starts to move after top dead center, the effective pressure of the gas combustion is absorbed onto the piston head, transmitting dynamic force onto the piston, for which the force exerted on the piston is equal to the pressure in PSI of the gas pressure times the piston head surface area. So 1 pound per square inch of pressure times 1 square inch equals 1 pound of dynamic force applied to the piston. This then transmits the dynamic linear force into rotational work to the crankshaft. This pressure that the air-fuel combustion pressure exerts on the piston head is known as BMEP, also known as brake mean effective pressure, measured in pounds per square inch. This is directly proportional to the torque and the brake horsepower that will transmit to the engine's crankshaft. So after the piston moves down on the power stroke, it then returns back up on the exhaust stroke, for which the exhaust valve will open up and purge the spent fuel air charge out of the exhaust port to the exhaust manifold out of the engine's exhaust system. So that completes one duty cycle of the four-stroke gasoline piston engine, for which 2 revolutions of the crank take place for every 1 power stroke. So that is the definition of the four-stroke gasoline piston engine. The 4 strokes have nothing to do with the number of cylinders, but they refer to the piston stroke cycles to complete one duty cycle. So now it is important to understand that on any type of engine or motor, there exist 3 types of horsepowers. there is the indicated horsepower. This is the sum of the total power involved in the engine or motor. This is a sum of the usable power available at the shaft, also known as brake horsepower, plus the power lost to keep the engine running, also known as friction horsepower. When these two are added together, the total power involved in the engine in terms of both losses and gains are calculated. So unless an engine or motor lists bhp, it is not the actual usable power output of the engine. So this video is going to focus on presenting a verbal explanation of how to properly rate the true power output of a 4-stroke gasoline piston engine. You must focus on the brake horsepower, the brake mean effective pressure, and the foot-pounds of torque at a given RPM. Very important. So the first thing you do is you locate the maximum torque rating in foot-pounds at a given RPM. After you do that, you need to take the displacement of the engine. If it's in liters, you need to calculate and convert the liters to cc's, cubic centimeters, and then convert the cc's to cubic inches volume. So let's say you have a 3.6 liter 4-stroke gasoline piston engine. That would equal 3,600 cc's, since 1 liter is equal to 1,000 cc's. Then you take the cc's, cubic centimeters, and you multiply that times 0.061, 0.061. When you do so, you will convert the cc's to cubic inches. So write down the foot-pounds torque max rating at the given RPM. Then write down the cubic inch displacement. Then after that, you need to access the engine's bore and stroke in inches. Let's say the engine is 3.7 inches by 3.4 inches bore and stroke. You need to then calculate the piston head surface area by taking the bore diameter in inches, dividing it by 2, squaring that value, and then multiplying it times pi, or 3.14. That will give you the square inches piston head surface area. Next, you have to convert the piston stroke in inches to piston stroke in feet. So let's say it's 3.4 inches of piston stroke. You would divide that by 12. This would give you the piston stroke in feet. After that, you're ready to now mathematically calculate the VMEP in pounds per square inch, which is equal to the foot-pounds torque rating divided by the cubic inch displacement multiplied times 150.8. This will give you the brake mean effective pressure in PSI exerted on the piston during each power stroke. Next, you take the BMEP value, you multiply it times the piston stroke length in feet, then you multiply it times the piston head surface area in square inches, then you multiply it by the number of power strokes per minute, which is equal to 1/2 the RPM only in a 4-stroke piston engine, which, let's say it was 150 foot-pounds torque maximum at 3,000 RPM. This implies that any RPM greater than or less than 3,000 RPM will decrease the foot-pounds torque rating from its maximum. This is called the torque curve. So we use that 3,000, we divide it by 2. This will allow you to calculate the power strokes per minute. So it'd be 1,500, 3,000 divided by 2. Then you take those 4 values and you multiply it times the number of cylinders. After doing that, you divide it into 33,000 foot-pounds per minute, which is the number of foot-pounds per 1 minute, equaling 1 horsepower. You need to use foot-pounds per minute, not foot-pounds per second, because RPM is involved. So 550 foot-pounds per second is equal to 1 horsepower, multiplied times 60 seconds is the foot-pounds per minute rating, which equals 1 horsepower. So once you multiply those 5 values out, divide it by 33,000, this will translate into the actual usable power available at the crankshaft. In this case, at the maximum rated foot-pounds torque, which is in this particular engine 3,000 RPM. So that is the correct way to actually rate the true power output of a gasoline 4-stroke piston engine. Keep in mind that when a gas piston engine is running, especially a gasoline piston engine, which operates on much lower compression than a diesel piston engine, will only have a thermal efficiency when running under no load at idle of around 33%. That is because 1/3 of the energy stored in the gasoline is lost out of the engine's exhaust in the form of waste heat. Another 1/3 is used to heat the engine block. Only 1/3 remains to move the piston down on the power stroke. So this means that after the engine is put under a load to move the vehicle or the application, it will lose more efficiency. On the typical moving automobile at 70 miles per hour on the freeway, the typical overall brake thermal efficiency is no greater than 20% or less, because you have to overcome the losses from tire rolling resistance and aerodynamic drag, not to include the uphill or downhill losses or gains. Now you gain, of course, efficiency down a hill. It's the sine degree of the degree of the road subtracted or added to the required power to move the vehicle at a certain speed during cruise. But going up a hill, of course, you have to fight gravity. Now, in terms of the stored energy in gasoline, there is exactly 20,000 BTU per 1 pound of gasoline, and 1 US gallon of gasoline weighs 6 pounds per 1 US gallon. So this means there's 120,000 BTU per 1 US gallon of gasoline. And if you release 1 BTU of heat per 1 minute, that translates to 17.6 watts of mechanical power equivalent. So it's easy now to do the calculations and find out the efficiency curves given the applicable OEM engineering specifications are listed for the given type of engine. Thanks for watching this video lecture, and look for the other videos covering the 2-stroke gasoline piston engine, 4-stroke diesel piston engine, and 2-stroke diesel piston in my YouTube video library. Again, thanks for watching this video and have a great day.